the Euclidean space is going to be a Lie group under vector addition. It is. And the unicircle is also a Lie group with the multiplication from the multiplicative group of complex numbers. And the third one is an interesting one. The n torus, n-hold torus, for a positive n is the Lie group, which, that's a typo, which is the product of the Lie group S1 with itself n times, right? So it's Lie group generated by the product of Lie groups. So yeah, those are examples. Okay, now we'll see what a Lie algebra is. Of course, like you don't really need to know about Lie groups to do Lie algebras. It's just that like the algebras need kind of a Lie group, so that's why I mentioned it. But a Lie algebra is basically an algebra over a field. Is a vector space, and the vector space has this bilinear operation, which is called the Lie bracket or the commutator, whatever you want to call it. And the commutator has specific properties that whenever you have two entries same, so you know, if you're just taking the commutator of a and a, then that gives you 0 for every a, right? And then you have the adjoint function. It's kind of the operation in the algebra, product in the algebra, is the adjoint map, and that is a derivation, right? And well, what's the derivation? Well, a derivation is basically a linear map between algebras which satisfies the Leibniz rule. So the Leibniz rule essentially is an abstract version of the product rule you see in differential calculus. So when you apply D to the product of B and W from the algebra, so here the bullet means the product in the algebra, is equal to D of V product W plus V product D of W, right? That's the Leibniz rule. And you can have this for various structures. Doesn't have to depend just on Lie algebras. It can be between algebras with other products, different products. You just have to be careful about how you're defining the product. So immediately from the two axioms that we set for the Lie algebra, we can see a few things. If you have this condition that the commutator gives you 0 whenever you have two same entries, then as our Lie bracket is a bilinear operation, we can use whatever we used, remember, with bilinear forms. We can use that here, right? So we can say a plus b taking the commutator is equal to a plus ab plus va plus bb, right? That's from the definition of a bilinear form. And when your a is equal to 0, you get this. Oh, I've messed up the variables vu with ab, but yeah, you're going to get ab is equal to minus of va. Let me fix that. Okay. So yeah, that's pretty much it. Now from the second axiom, what we can do is we can use the fact that our adjoint function is a derivation, and we can apply that on this. So we say ABC, right? So ABC is the adjoint of BC with respect to A, right? Because that's what the adjoint function does. It takes an element and it puts it into the commutator bracket. Right? So that's what we're doing here. Then that is equal to the adjoint of C with respect to AB, and plus adjoint of AC with respect to B. Yeah, that's just from the fact that it is a derivation, and we use this Leibniz rule. So this turns out into this nice cyclic subtraction equals to 0, and this is called the Jacobi identity. And this Jacobi identity is kind of like an important thing to check when you're checking something is a Lie algebra or not. Right? You need to check if the product, if the bracket for that algebra has this condition, satisfies this condition. Schuler doesn't talk about this in lecture 13, or does he? I don't remember. Probably he talks about it in very early lectures.
About the Jacobi identity?
Yeah.
I can't remember whether that's at the end of 13 or beginning of 14. But he was talking about the adjoint.
Right.
I think adjoint was in the 14.
Yep, adjoint was in the 14. Regarding derivation and Jacobi identity, he has talked about it before when he was introducing algebras, and he gave Lie algebra as an example. Or maybe in 13.
Yeah, I had to flip back to an earlier lecture when he had talked about the bracket of vector fields.
Right.
Or of homomorphisms of vector fields. Or maybe I should say automorphisms. If you had two automorphisms, phi and c, then the bracket was defined to be phi composed with c minus the opposite composition.
Yep. Okay. Okay. Yeah, that's your Jacobi identity. A Lie homomorphism is basically a homomorphism between two Lie algebras which satisfies the homomorphism condition for the commutator, the Lie bracket. Right? So it preserves the Lie bracket. So f of this bracket of AB is equal to bracket of FA FB. That's the homomorphism. Then we consider like all other algebraic structures. What's an ideal of a Lie algebra? Well, an ideal of a Lie algebra is a Lie subalgebra. So here I've written subspace. I'll change it into subalgebra actually, such that for when you take the commutator of every element, right, of every element in G, the algebra, and every element, so this is again a type of A is going to be in I. This can't be the case otherwise.
Yeah, I think that I did myself a disservice when I was just trying as a shorthand to think of an algebra as a vector space with a multiplication. Because the word multiplication is kind of loaded.
Mm-hmm.
I mean, for example, if I say multiplication, you're going to assume associativity.
Right.
I mean, any reasonable multiplication is associative, right? Well,
No.
not in this sense. it's another rule of composition, but it's good to probably call it something other than multiplication.
Right, right.
It's for tonight. Yeah, is that what you said?
Mm-hmm.
Rodman calls it a not necessarily associative algebra.
Right?
That's not true.
But somehow putting up a warning flag. And then Rotman or someone was just bringing up the cross product in R3 as an example. It's like, oh,
Probably Rodman. Rodman actually, yeah, Rodman, that's Rodman. Rodman has some examples this time.
oh yeah, there it is.
Yeah. He talks about the GL, general linear group, which is also Lie algebra. Schuler talks about it in lecture 13.
Actually, little GL is all matrices rather than the invertible ones.
Is it?
Yeah, the
So it's
tangent
not
space
okay.
too. Yeah.
Okay. The notation confused me, I see.
The invertible matrices are an open subset of the set of all n by n matrices, so they have the same dimension.
Makes sense. Right, okay, so this is, yeah, the matrices of n by n, okay.
Of course, he doesn't explain this notation. It's like, why would we call it GL?
Wow.
Or weird Gothic GL.
He gives the set of all derivations with the bracket as a Lie algebra. Interesting stuff. All the algebras of a field, K, form, and category. So that was what the lecture was that I was watching was talking about. Then he comes back to usual stuff. Ideals, simple.
Yeah, Schuler started talking about ideal.
Right, lecture 14.
Yeah.
How far do you think you did see? Did you see Curtown's criterion?
No.
Okay, so that's probably. Did you see killing forms?
That's where I left off. I saw him
yeah, makes sense.
define the killing form.
Right. Over the adjoint map. Probably that's not a bad idea if we do it. Do we need any differential geometry stuff for killing forms? I mean, of course, it comes up in differential geometry, but can you do it pure algebra?
Well, it's the trace of a linear map, so that sounds like algebra.
Yeah, it's not like
and the adjoint map is purely algebraic, right?
Right. I think we can. I have the notes. We'll probably get there.
Now what? I can't remember a way of figuring out the trace without appealing to a basis. And he said, Schuller said that he was about to show what all this was like in coordinates, but he was going to do some coordinate-free stuff first.
Yeah, he comes
So I
to
did
that.
not make it as far as seeing
Right.
what this looked like in coordinates.
In coordinates, it looks pretty messy. But yes, he proves some propositions about the filling forms, and then he goes into a few other things with the spaces. So this is where he goes into the component stuff. The lecture notes are amazingly well written. Okay, let's do a few things with Rotman stuff. If we can get into the, what is it called? The Engels theorem that he's... that's the thing about Rotman, right? He doesn't explain anything. Like, he just says, Engels theorem, see Humphreys. For the proof. Well, if we were to see it there, why would he bring it up? But yeah, so we talked about ideals. Ideal of a Lie algebra is a sum algebra, which such that when you take every element of the algebra in the first entry and every element of the ideal in the second entry, that stays within the ideal. Right? So in all cases, this commutator stays in the ideal. The Lie algebra is not always commutative, right? That is anti-commutativity, shows that every left ideal, like left ideal of rings or other modules, is necessarily a right ideal. That is, every ideal is actually two-sided. That's what anti-commutativity gives you. So this is interesting, you know, commutative property gives you the two-sided ideal, but anti-commutative property is also giving you two-sided ideals. So yeah. So what are our trivial ideals? Well, our trivial ideal is of course the zero ideal and the whole the algebra itself, the L. So 0 and L are the trivial ideals. And when do you call a Lie algebra is simple? Well, you call it simple if it is non-abelian and it contains no non-trivial ideals. So the only ideals that are possible are the trivial ideals. That's a simple Lie algebra. I believe Schuller mentions it, that there's something called a semi-simple Lie algebra when it contains no non-trivial abelian ideals, right? So it's like your ideals are of course trivial, but they're abelian.
I may have misunderstood him. I thought that semi-simple meant that it was the direct sum of a bunch of simple ones.
That's that's probably semi-direct sum you're talking about. Oh wait,
I have a
it's the decomposition or something
mental
like that.
picture.
Yeah, probably. Yeah, okay, so yeah, there's this proposition he proves which says that Lie algebra is simple, semi-simple, if and only if it can be expressed as a direct sum. So you're right, it's just a proposition.
Oh, okay. Oh yeah, that was in 14. I wasn't understanding everything. I just kind of noticed his underlining it.
Right. Some terminology in Rotman which might be helpful. You have something called a quotient. with respect to an ideal in a Lie algebra. So L mod I is the quotient space when L is a vector space and I is a subspace with bracket that is defined like the cosets we always define. Right? You have to check that this bracket is well defined on L mod I, and because of the anti-commutativity of the bracket, it works out. A few of the things that we probably do need. The kernel, when you have a Lie homomorphism, the kernel is the same thing. Everything that goes to 0, it maps to 0. Kernel of homomorphism is going to be an ideal in the Lie algebra. Then, we have, the canonical stuff, the canonical morphisms that go from something to mod of something. Here you have the natural map V going from L to L mod I, and it's defined by taking A to A plus your ideal, which is being modded out, right? And interesting, what makes me think about this is, do you have some kind of isomorphism theorem for this? If you have two ideals in Lie algebra, how do you multiply them? Well, ij is equal to the summation of all these brackets with respect to the specific i's and specific j's from the respective ideals. When you multiply L with L, so that's your trivial ideal L with itself, you get L squared, and as the analog for Lie algebras of the commutator subgroup of a group. Okay. And L squared is going to be 0 if and only if L is abelian. Okay, so then your product is going to vanish. It's going to okay, going on. When do you call Lie? Okay, so we're going to call something solvable, but before that, we are going to have a derived series. So the derived series of Lie algebra L is defined inductively like this. So L0 is equal to L, Ln plus 1 is equal to Ln squared, right? So Ln squared, okay.
Yeah, this is Schuler wrote this down kind of the messy way. He did it like, first of all, you have L bracket L, and then you have L bracket L bracket L bracket L. Then you have that thing bracket itself.
Right. He defined.
And the question is, do you eventually get down to 0?
Yeah, but to be honest, that made kind of sense to me because he was using containment, and
yes,
that would look something more intuitive. But I don't know. This also looks good.
no, I know we've seen stuff like this before, but it's still not meaningful to me. We probably even used the same terminology. We probably called it solvable there also.
Solvable groups, remember? Rotman again.
Yeah.
Yeah, at some point we'll have to do some review. God, there's a lot to review. Yeah. Anyway, so this is your derived series of a Lie algebra, and you call a Lie algebra solvable if there is some positive n for which, when you take the power, you get the trivial 0 ideal. So that's your solvable stuff. Let's see. So there's an analog for Lie algebras of the descending central series of a group. The descending central series is defined inductively because L1 is equal to L, Ln plus 1 is equal to L times Ln. Okay. And a Lie algebra is called nilpotent. There is some positive n for which Ln is your zero ideal. I believe that, yeah, Jacobson has a chapter on this. It might be a good thing to look at. Let me see how this treatment is.
Didn't Schuller attribute the big theorem he was going over to Levy?
Yes, probably.
I haven't seen his name come up in these other references. Maybe we just haven't gotten there yet.
The decomposition theorem of Levy.
Yeah.
I think I saw it somewhere.
It's probably a big hard one.
Levy. Yeah, you have the Levy radical splitting theorem. Hardens the algebra.
There it is. Maybe.
The theorem asserts that if B is a finite dimension, the algebra of characteristic 0. Characteristic 0 condition was not by Schuller, I believe. But yeah, with solvable radical.
Oh. So in Schuller, he called the radical R.
Yes.
Instead of squirrely S here. He didn't call it the radical.
Oh, that the solvable.
But he called it like the solvable part. Yeah.
Yeah.
And then the other part was the semi-simple part, which was the direct sum of the simple algebras. Or subalgebras.
God, the notation of Jacobson never gets better. There's something called the Whitehead bracket too, which came up in that lecture that I was watching, and it's a pretty interesting thing. It is kind of a modification of the Lie bracket, but it's way more interesting than that. But yeah, Jacobson can be a thing to look into with the stuff. So that's the terminology we kind of need. From here, I think I'll move into Schuller's notes, and we'll see how far we can go with it. If we can do Dinkin diagrams, that's good. Otherwise, we'll see. Yeah, this is lecture 14. Do I have a recording of lecture 14? I probably, yeah, at some point I downloaded not all, some of the lectures. Lecture 14 was on the...
When he numbers things in the lecture, they're not going along with the notes, the numberings. Is there a textbook that matches the numbering off? Like he writes 5.3 up at the top, and it's not 5.3 in the notes.
Right. And the notes are like lecture number based. The thing is, these notes were not even made by someone who attended lectures, like in person. He was like a guy on the internet who watched these lectures and made these notes. It's the amount of commitment. But he doesn't put any information about the course itself. It doesn't say what books he's following. It doesn't say, like, there are problem sets, problem sheets, he says, which we don't have access to. But, yeah.
Yes, somebody mentioned that he was following Lee, and I went and looked. It's like, I'm not sure this matches up with Lee.
It doesn't? Which book of Lee would it match with?
The person in the comments said the Smooth Manifolds book.
The Smooth Manifolds book. I remember it doesn't have much of Lee stuff. No. I think in the notes, if you see, the notes have a bibliography or something like that, references. And the guy tells you, I think like this was like first time when I saw, okay, these are cool books, I'll go into each of these cool stuff.
Oh, there's the Hall book.
Which one?
I see that the Hall book is in the index, or the references.
The Hall?
That you were just showing to me, the one on Lee groups.
Okay.
Oh no, maybe that's a different one. Lee groups lay algebras and representations.
Let's see. But yeah, this has some stuff. Which is good. Yeah. I was reading this one earlier today for Lee stuff. This has a lot of things on Lee groups. Warner. Yeah, on Lee groups, yeah, he has how. Okay, interesting. Fulton Harris.
I saw somebody else mention that as a reference for this stuff, but I haven't looked into it.
Yeah. So, wait. So we are pretty much done with up until the solvable part of Euler. Let's see when he defines the semi-direct sum, the Levy theorem, and we'll see. So this theorem, he doesn't state the proof of that, right? The proof of Levy, no. Okay, so...
Yeah, Fulton and Harris prove Levy's theorem in an appendix.
In an appendix?
Yeah, Appendix E. And of course, somehow they managed to do it in 2 pages. Yeah, there are like 16 chapters on Lie groups and Lie algebras.
Important.
I mean, it looks like most of the book, actually.
Right. Representation theory. Okay. So the direct sum, as Schuler defines, as if you have two algebras, Lie algebras L1 and L2, the direct sum has the vector space direct sum as its underlying like vector space. So the direct sum L1 O plus L2 as Lie algebras has L1 O plus L2 as vector spaces as its underlying vector space. And on that, you define all the brackets. So this kind of makes things easier because we wouldn't have to worry about the field and whatnot, as Rotman seems to be worried about. But vector space with bilinear bracket makes sense. So this is how your bilinear bracket is defined for this direct sum. Pretty trivial. So what we can do, he says, when we identify L1 and L2, the subspace is L1 O plus 0 and 0 O plus L2 of L1 O plus L2 respectively. We require that when we take the bracket of L1 and L2 as Lie algebras, and this bracket is defined on the direct sum of Lie algebras, then that happens to be 0, just like we needed AA to be 0, remember? As the definition of Lie algebras. And I believe Schuler kind of makes it difficult by using this subscript and whatnot, but I guess it does his job. So.
This feels like an orthogonality kind of condition.
Right, yeah, on the vector space. And it's kind of related to what we were doing with bilinear forms. It's not that different.
Mm-hmm.
Mm-hmm. Okay, now he goes on to define what a semi-direct sum is. Well, okay, so semi-direct sum is where you have two algebras, Lie algebras R and L, and R semi-direct L has R direct L as its underlying vector space, and the Lie bracket that what it needs to satisfy is that bracket of RL is going to be subspace of R, right? And what this means is that R is an ideal of the semi-direct sum. What do we need all this for? Well, we need all this for the Levy stuff. So the Levy theorem, classification theorem, not classification, it's the decomposition theorem, says that any finite dimensional complex Lie algebra can be decomposed as a semi-direct sum of a solvable Lie algebra or semi-direct sum with the direct sum of n Lie algebras, simple Lie algebras. So those are your L1 till Ln, right? That's the Levy decomposition theorem. I don't know where to find the proof, but you said it's in Fulton Harris. Looks interesting.
Seems so. At least that seems to be what he asserts that they assert that they're doing on page 499.
Is the proof too bad?
Oh yeah.
Okay. Then he provides this proposition. Okay, the proposition says that Lie algebra is going to be simple if and only if it can be expressed as a direct sum of simple Lie algebras, right? And that is the main kind of theorem. Which he doesn't prove, but he uses it later. Okay, yeah, sorry, I'm back. Yeah, so that's proposition for Schiller. We go back into other things. We see the adjoint map and the killing form. Let's see a bit about that. So the adjoint map is something we've already seen. We know that it's a bilinear thing, and that it's something that you need for the algebra. The proposition 14.5 shows that the adjoint map from the algebra to its to this endomorphism of Lie algebras is a Lie algebra homomorphism, right? So you have to check that it preserves the brackets. And the step-by-step process to prove this is just putting one of the definitions, putting one of the conditions, and following through. There's nothing much in there. Okay, so if now he defines what a killing form is. If you have a Lie algebra over K, then the kappa, I believe that's the symbol name. The kappa is the map, bilinear map, the K bilinear map from L cross L to K, just like any other action you would have, right? And what it does is it takes an ordered pair from your Lie algebra and maps it onto the killing form applied to them, which is defined as the trace of the adjoint map on those elements, right? So kappa of xy is equal to the trace of the adjoint of x composition the adjoint of y. That is a very interesting thing, and the trace is our usual vector space trace. He mentions it how the killing form is not like the differential form or anything like that. Differential forms are antisymmetric. Kappa is symmetric if L is finite dimensional, right? So kappa of xy is equal to kappa of yx. You can also see how that would work because the trace is cyclic and also the composition works out. So another thing that he mentions is that the killing form is associative with respect to the bracket. So if we have a Lie algebra for any xyz, if we apply the killing form to bracket xy and z, that is equal to killing form applied on x bracket yz, right? And you have to again follow each definition and apply things step by step. And so what here you apply the definition of the killing form you get here, then you apply the definition of the adjoint map and you get here, right? So the trace of adjoint x, adjoint y, that's the adjoint map. Then you apply the definition of the bracket to expand this into this, right? Then your trace is you're going to have this minus, so your traces are going to divide from here. So you'll have add x, add y, add z, and add y, add x, add z, taken traces. You change the ordering a bit because of you change the ordering because you can do that over trace. Yeah, it's a cyclic thing. Yeah. Then
what does he mean by that?
Which one?
The trace is cyclic. What does that mean?
The trace being cyclic, I believe, means that when you're taking the, like, remember, like, if you think about the traces, like all the things in the diagonal, so like you would have, if you change the places of things in the diagonal, it still stays the same. So if you change like the top left thing and the top bottom right thing, the trace stays the same. I believe that's the thing it's talking about.
So if we commute two matrices, does that just permute the diagonal entries?
I guess. You have to I believe you'll have to do things with the permutation again, which I'm not sure how to do that, but you'll have to like take a bunch of matrices. You will have to apply their indices to this permutation, and that probably leads to cyclic. But as I understand, it just means that the trace of AB is equal to the trace of B. No, not that. Trace of AB CD is equal to trace of BCDA, CDAB, and DABC. Essentially, if you change the matrices' order, it works out.
Yeah, I'm game. I mean, I believe that. I just hadn't ever heard that referred to as trace being cyclic. I was unfamiliar with that phrase. But yeah, I'll buy that trace of AB is trace of BA.
Right. Okay. And that's probably all we need here during the composition.
Yeah, that seems to be the key step later on where...
Yeah, then he takes the trace of all of this. Then he takes, then he applies the definition of the bracket again. Essentially just manipulation to get to where you want to. It's nothing else. Using the right definitions, of course, the properties. Okay, then coming to Cartan's criterion. What is Cartan's criterion? It says that a Lie algebra L is simple if and only if the Killing form is non-degenerate. So that means if your Killing form gives you 0, that means the first entry is 0. That implies that. So kappa of xy being 0 implies x is 0. Okay, so we'll try to see what our symmetric bilinear form is. We've already seen this. There's nothing interesting about it. But he's stating how the Killing form also kind of has that. So the associativity property of kappa with respect to the bracket can be restated by saying that for any z in L, the linear map, this adjoint of z is anti-symmetric with respect to kappa. That is, xy in L is kappa of at z x comma y, yes, is equal to minus of kappa of the other way around. Right? But if we want to do like actual computation over the Killing form, we would need some kind of basis, right? Because we're working over vector spaces. So if you have a Lie algebra over K, you take a basis EI, then we have the bracket of EI, EJ as CKIJ. Okay, this is pretty cool. This is actually very similar to doing tensors with a basis and like the actual way it should be done than what we did. that's pretty much the same. So when you have a basis, you define that when you take the bracket of two elements of the basis, you can write them in this manner. And your C's are like things from the field, right? And they're called the structure constants of the Lie algebra with respect to the spaces. So
I'm only asking because the notation looks similar, but are these related to the Christoffel symbols for a manifold?
I don't think so. I mean, it does look
It's just
similar.
got the same pattern of superscripts and subscripts.
That's why I call like it looks a lot like the tensors you do in like differential geometry. But I don't think if it's exactly related to that.
Cool.
As our bracket is antisymmetric, our constants are going to change their signs when we change the places of the indices. So ckij is equal to minus of ckji. Right? And the Jacobi identity, as we saw, is going to be something like this, which I don't want to read, but it looks very familiar when you put in things. And you're going to get the indices in the cyclic order changing, right? He has a few propositions after the which would help us compute a few things. Then it goes on to the while group and the fundamental groups, which are both probably interesting things, which you also see in representation theory, I believe. But I'm not sure if we would be able to cover that. If not, I think it's better to keep that to Thursday. We'll see.
I just found an answer to that question.
Which one?
On Stack, my question about the Christoffel symbols.
Christoffel? Okay.
So they're not the same, but they're related.
Interesting.
I'll just paste the answer into the chat.
That will give some motivation about all the stuff. If you study the Lie group, G is a manifold with a basis of tangent space in B. G, you have the definition of Christoffel symbols in G like this. The structure constants are like this. Let's define the metric on the Lie group from the adjoint action like this. And using the metric G to lower the index, we have this. Okay. Use some cos-zoo formula. Interesting.
I don't remember what that means, but it just shows that you can express one set of constants in terms of the other. Or so it appears.
Yeah, he mentions Kobayashi and Namizu. I remember that they wrote like 2 volumes in differential geometry, which I haven't thoroughly checked, but they are classics.
And very dense.
Someone called
so it's like my second year as an undergraduate, and I didn't know any better. So when in the bookstore there were required books and recommended books, I bought them all. And these had been listed as recommended books, not that the teacher ever referred to them one time. So they're on the bookshelf, and I've never read them past the first couple pages.
Second year of undergrad on Kobayashi. That's a nice story.
No, we didn't do it. I take it back. That was third year. I did topology second year, geometry third.
That's pretty cool, to be honest. Like back in those days, you were pretty ahead of most undergrad students. Yes.
Yeah. Fortunately, there were enough of us, like a critical mass, that the classes made.
Mm-hmm.
So, and there was a mix of undergraduates and graduate students in the classes, but I was with other people who had exactly the same background as me, because we were taking the same calculus class, same topology classes. Pretty much going through it all together. It was awesome.
Interesting, yeah. Where did
including an 8-year-old.
8-year-old?
There was an 8-year-old in the class named Ralph. He was around for the first couple of years, and then his parents pulled him back out again.
Take him. He was taking which classes?
I can't. I know that he did the first 2 years. He did the calculus and the topology and differential topology. I don't remember whether he was around for the geometry or not. I've forgotten.
Good lord. Well, that's the best thing about American education. Anyone can go and sit in the university. What did most people in your class went ahead and do, academic research?
There weren't many that I kept up with. I mean, we all went different places for grad school. But one guy, he definitely went into research, and he taught at the school that I went to grad school at after I had left. After I left, they hired him as a teacher for a while.
I see.
And some of the people that I went to grad school with, they definitely went into research. Others went into oil and gas. They went into industry.
Into industry. Yeah. I mean,
so I'll admit, I'm not getting a great. I say I'm not getting a great idea about what these add maps and the killing forms are doing. I mean, I saw the definition. The definition seems simple enough, but I'm not clear what they're used for.
Right.
No, I mean, here we have a way of calculating them, so that's something.
Yeah. So here you're just breaking things down into components. You say add EI of KJ, what notation gone, is equal to CKIJ, and kappa IJ is equal to CMIK CKJM. This is like tensors again. Yeah. That's what the proposition says, and something you would expect, but let's see how it's proved. You take a dual basis to original basis. What you do is you expand this thing. So you can write that as I think this is something that Schuler talks about in the very early lectures when he's talking about tensors. That the upper subscripts, so superscripts, are for the basis indices, and the subscripts are for the basis elements, the vectors, covectors and vectors. So he uses this epsilon k for his denoting the dual basis elements. So epsilon k of the adjoint of EI of EJ, right? And as you said, like this is nothing really to understand, but it's mostly like following the notation. Then you expand the definition of adjoint, you get the bracket, you expand the bracket in terms of CM and the whatever here. Then you pull CM, the structural constants, the structure constants out of the brackets. You have epsilon k em, and like tensors that falls down to the delta. I'm forgetting which delta that is. The
Kronecker?
Yeah, Kronecker delta. Yeah. So that's the Kronecker delta. And that's pretty much the goal. Like with Schuler, he's always trying to like represent the basis elements, doing components in this manner using the indices and the Kronecker delta all the time. Yeah. So for the second one, he uses the kind of like the matrix representation, but yeah. So he says, recall from linear algebra that if V is finite dimensional, then you have an endomorphism. We have the trace of the endomorphism as PKK. P is the big P. He is the matrix representing the linear map for some basis. Then the matrix representing P circ C is a product matrix multiplication of capital P, capital C. Using these, what you do is you say, okay, kappa ij is equal to kappa over our basis elements EI and EJ. And then you say, okay, EI, AJ, sorry, this whole thing, kappa with this EI, EJ is basically just the trace of the composition of the adjoint map of EI and EJ. Yeah. And then you put you say, okay, the trace is basically trace is basically having, wait, what is this notation?
So summation notation, summation convention there.
Yeah, okay, yeah. The hidden summation. Okay,
So it's like summing over the diagonal entries.
Yeah. After being used to Rotman, this seems weird. And then you break this down into MKKM, like tensors again. The indices are totally like tensors. And you expand the definition of adjoints in each of the cases, you get this. Works out. And then for the next 2 pages, 3 or 2 pages, not 3 to 4 pages, I believe. He talks about the while group, the fundamental roots, all of which I believe can be good things to know about before we get into the Dinkin diagrams, which are interesting. Which I believe we'll have to leave for Thursday. And what you can do is follow these notes and Schuler's lecture 14. I'll make my own notes by the time, and from these we'll have something in the preset.
Sounds good.
And for tomorrow's preset discussion, if you have something, submit. I'll try to write my preset solutions like last time, and I'll post it in the chat. So that'll be some kind of discussion later. Yeah.
Yeah, sounds good. Sorry about disrupting things, but I am
No, it's okay.
eager to keep moving.
Yep. And from next week we'll start differential topology, and we'll start fields and Galois theory. Both of those things I need to organize a bit, and we'll spend time with Galois theory. That'll be probably more interesting than whatever we've done until now. And after a few weeks of Galois, we'll go into reviewing modules from all the terrible things we have done before we get into ATIA or anything commutative algebra. So yeah.
Yeah, one of my goals in the Galois theory is to actually be able to compute some Galois groups and explicitly see the Galois correspondence. So that'll be something to work toward. I noticed that Ian Stewart made a huge change between the second and third edition of his book. I just downloaded the fourth edition a couple of days ago, and I was comparing it to the Ian Stewart's Galois theory book.
Oh, Galois theory, Ian Stewart. Okay.
It's in the fourth edition now.
He's made some severe changes.
Yeah. In the second edition, he starts off over general fields, and in the newer editions, he spends like 15 chapters working over subfields of the complex numbers, and then goes to general fields.
God, how long is that book?
It added 100 pages. So the second edition was 200 pages, and the fourth edition is 300 pages.
Damn. Interesting.
That's funny, I don't see the fourth edition right there. Oh yeah, that's there.
Yep, it's there.
Yeah.
Is it good, the book?
You'll enjoy the first introductory chapter, which is historical. But I like him as an author.
Okay.
And he has good exercises. I think that you might prefer the second edition over the fourth, just because a lot of the beginning chapters in the new edition are elementary. I was starting to skim through them to see, how many chapters I could jump before I got to something interesting, but I didn't spend enough time to figure that out.
Okay.
But like in the second edition, there's already interesting stuff happening in chapter 1 or chapter 2.
I see.
I think that with this edition, the fourth edition, there's going to be a lot more to skip over.
Makes sense.
Which is fine. I mean, it's good. Although there might be some particular computations that are interesting.
I am kind of interested in Roman's field theory book. I haven't taken a deeper look into it, so I don't know. We'll try to go through Artin, and I'll see what else we can supplement it with them. Because Artin kind of looks very neat, and we'll have to have something for exercises, though he doesn't have exercises.
Right.
Okay then. You have a good time. Safe trip. And
yeah. Thanks for typing up some notes for this stuff.
Yeah, I'm going to.
And for pointing me toward the Schuler. Those are excellent lectures.
Right. Yes. We'll meet next week, hopefully on Monday, and start some topology.
Sounds good. Whatever you post over the weekend, I'll comment on. I'll check it out and let you know how well prepared I can be for Monday.
Okay. Yeah.
Sounds good. Take care.
Yeah. See ya.